Next up, in this video, we'll talk about the exceptional circumstances our code can end up in and how to handle it. That is, we'll talk about exceptions and exception handling. When we write code, lots of things can go wrong. For example, trying to read from a file that isn't there, or accessing a list that's out of bounds, or adding a string to an integer. When these things happen, they're called exceptions. Here's a table of some of the different exceptions we've already seen. Now, to manage these exceptions when they occur, we've seen that we can use error checking as one solution. So we'd say, if not some error condition, then do the work. Else, we have some default value or a helpful error message or something that gracefully controls that circumstance to prevent our code from crashing. There are many different error conditions to check for. We've seen, for example, type checking, where we ask if some variable is of type, let's say, integer, then we'll handle it as an integer. If it's of a different type, then we'll handle it that way instead. We've also seen value checking, where we ask, for example, is some string a digit before attempting to convert it into one? Or asking, is the value of some number greater or less than 0 before assuming it's a positive or negative number. While these approaches do work, code full of these checks quickly become messy and cumbersome. It becomes difficult to separate the process that we're trying to accomplish from the checks that make sure it's safe to do so. Python, and most other languages, offer exception handling as an alternative. Exception handling is a built-in syntax for catching errors when they happen and handling them accordingly. This provides a consistent and clean syntax for handling all different types of errors, and separates the error handling from the main process. This keeps our code both clean and safe, so it's easier to maintain and has fewer errors. The syntax for exception handling in Python is as follows. We start with the keyword try, which is the entire statement for that line, and then a body of code, which would be the normal code that you're trying to execute for your program that might result in some sort of exception. So for example, in some system where we're asking the user to enter a number, the try block would be where we convert that user input from the string that they gave us into the integer that we asked for. Following that block of code, then there's the keyword except, and then another block of code which contains all of the operations that will happen in the situation where something went wrong. So the way this works is that Python will see the code in the try block, attempt to run through it, and if all goes well, that's all it will do. However, if something goes wrong while trying to run the code in the try block, it will stop running that code and jump to the exception block. At that point, it will run through the except code, which should hopefully handle that error in a graceful way. To demonstrate exceptions in practice, let's go back to our IDE and write a simple bill splitting program. So this program will take in the cost of some bill, let's say the check at the end of a restaurant meal with many friends, and we'll ask the user how many people we need to split this bill by, and then we'll just print out the total divided by the user's number. At its heart, a very simple program. So let's just write the base code without exceptions, and we'll see which exceptions we run into. So we'll say def split bill. That takes in some amount. This is the total amount of the bill. Now we need to ask the user how many people were at the table so we can split by that many people. So we'll say input how many people. Now that's supposed to be a number, so we'll say int whatever they've typed in, assuming the user types in good input here, and we'll store that in a variable, call that people. Once we have that, all we need to then do is divide the input amount by the number of people. So we'll say result equals amount divided by people, and then we'll report the result. So print result. And then we'll test this function out. We'll say split bill, and we'll pass in 100 as the amount. So save. Run our code, python exceptions.py. So we get our input here, how many people? And if I said 3, it takes 100 and it divides by 3. Perhaps we should do a bit of formatting there. So in our print, we could say, for example, an F string, and we'll print out $, and then the result, but then we'll make that a 0.2F, so it prints with 2 decimal places. And now if I say 3, each person has to pay $33.33. So that seems to work fine. We have a nice little output there. Code's all good so long as all of our inputs are good. But now if we run this code and give bad inputs, like if I said hello, then our code crashes. It says value error. We attempted to convert the string hello into an integer, and go figure that's not a number. So to address this issue, what we can do is use exception handling. So we can put a try block around all the code that we want to have execute, so all of our process code itself. And then if something goes wrong in there, we want to handle that error. So we'd say except, and this is where we would handle the error in whatever way we would need to do. This is like default values, error message, etc. The actual steps you'll take here are dependent on the problem at hand. In this case, we just asked the user for a number and they gave us a bad number, so we'll print out we couldn't do that. So print, that's not a number. Now when we run our code, we can still split the bill by as many people as we like. I should probably use a different number just to demonstrate we can do other values as well. But if I run this and I give a bad input, like the word hello, it says that's not a number, and it closes gracefully. So we get a meaningful error that's readable by a human, and our code never exhibits any of those exceptional situations. So walking through what actually happened, our input function here returned the string hello. We attempted to convert that to an integer, which didn't work. So rather than running these other lines, notice it didn't print out any result here. As soon as we got to this point here, when the error would have normally occurred, it jumps out of this block down to accept, and then does whatever we said in accept. In this case, just prints out that's not a number. So our code seems to work and it seems to be safe now. Let's try out some other edge cases. So I'll run my code one more time. And now what happens if I ask to divide our bill by 0 people? It says 0 is not a number. But that's not right. 0 is definitely a number. So in this case, what's happened is we've caught all possible exceptions, and we've assumed that it's the first type of exception, right? So we're saying catch any exception here and always say that's not a number. And that's because we thought the exception was this integer conversion. But if I pass in a 0, it gets past that line and it attempts to do a 0 division. Amount divided by 0 is an error. So the code would have crashed there, but we have a try except block, so instead it jumped down and printed out that's not a number. So we get the same error handling no matter which error comes in. So it's somewhat bad form to catch all exceptions like this because it catches unexpected ones as well. In order to catch specific exceptions, we can extend the try except syntax as follows. So the syntax still starts with our try block, which again is just the actual operational code. Following that, we can have as many except blocks as we want. Now, if we just say except as we've done without anything following, so except colon and then a body, that will catch all types of exceptions. However, if we include the name of the specific exception, then it will only catch that one type. In this way, we can specify different types of exceptions, each with different steps for handling those errors. This could mean anything from different values and different warning messages, all the way to completely separate functions being executed in response to these errors. In order to know what the name of an error is, you can see that in the crash report that we've seen. We also have it in this table here. So value error, type error, IO error, these are the names of the errors that you would put into your except block in order to catch these specific types of errors. So if we only want to catch the value error of converting a string to an integer, we could say catch value error, and then other things like a 0 division error wouldn't go into that except block. If we would like, we can specify explicitly that we're catching all types of exceptions by using the word exception. So we'd say except exception. And that's just catch the general type of exception, which is all type of exceptions. So the syntax is a bit like an elif, but for exceptions. We can distinguish between multiple different types and handle each one accordingly. If we'd like, we can also put the exception itself into a variable. For example, if we wanted to print out the error while still handling it gracefully, the syntax for that is except and then the type of exception. Then we use the keyword as and then some variable name. So here I called it my error. So if that's the variable name, then inside this block of code, if I refer to my error, I could say print my error, for example, then we can print out the error that occurred without our code screeching to a halt. So for example, if we only wanted to catch the error from converting our input into an integer, we could say except value error, and then we'd handle that error. So if we try this code, we want to divide by our bill by 6 people, that's fine. If we want to divide our bill by hello, it says that's not a number, which is the exception handling code here. And if we want to divide by 0 people, notice that didn't get caught by the same branch. And since we didn't have a branch for it, it resulted in a standard runtime error that crashed our code. We get 0 division error, division by 0. So here's the name of your type of error. Anytime your code crashes, you should get this label for your error, and then an English description, division by 0, or can't concatenate an int to a string. If you take this as the name, that's the thing you can put in your except block in order to catch it next time your code runs. So let's catch that one as well. all we have to do is just add another branch. So except zero division error. And in that case, we'll just print something like no zeros. Test this out, save and run our code. We get how many people. So if I had said hello still, that goes to the first branch. And if I say 0 instead, then it goes to the second branch. There's no runtime error crashing our code, and we're handling each one of these two types of errors separately. So even with this small example, we can see the advantage of using exception handling versus using if statements instead for our error checking. And let's solve this same problem without exceptions so we can see this alternative. So I can say def split bill2 takes in some amount. And this is going to do the exact same work. It's going to ask the user for a number, divide our input value by the number the user gives us, and print the result. The difference here is we now need to check for all of the errors at each stage. So the first step is we get our input. So we say people equals input, how many people. Notice we didn't immediately convert it to an integer because we need to first make sure what the user gave us was in fact integerable, if that was a word, able to be put into an integer. So say if people, which is a string, so it has string methods like .isDigit. So we check to see if the thing the user gave us can be a digit, and if so, then we'll say people equals the int of people. Okay, so now we have the integer from the user. We want to do the division, but they might have given us a 0 because a 0 is a digit, so we need to make sure of that as well, so we'd have to check that as well. If people does not equal 0, then we can do our math. Result equals amount divided by people. Oops, a couple of typos here. Amount divided by people, and then print the result. Note, this is a pretty small problem, but already the nesting of our if statements is taking over our code. So without the try block, the code for checking our errors is mixed in with the code for solving the actual problem. And because of that, our code becomes more difficult to read and more error prone. And if we wanted to print the errors for these, our code would be even longer with the else branches doing the print statements. So this split bill function catches all the exceptions that we're aware of, but let's see if I can't find one more here. So I'll say, still running the right function, python.exceptions, and it asks me how many people, but instead of typing anything, I'll put a keyboard interrupt. So we got a new exception of type keyboard interrupt, which doesn't need any description because that's just a keyboard interrupt. You decided to end this program. That's a good idea when developing your code, when in the debugging and designing process, to have your code crash when it reaches these errors so it doesn't continue on in bad states. That way we can, at that time, address those errors. But if you're releasing this code and it's important that it keeps running no matter what happens, then you can add an additional branch, just the generic except without any name, and that will catch all of the other things that could go wrong. So we'll just say print something went wrong. So now we're going to try to run through these 3 lines, and if something goes wrong, one of these 3 errors will pop out. Notice only one of these will ever happen because once we're in one of these except branches, it doesn't continue on with the next one afterward. It does this code, and then it goes to anything that's following the try except blocks, which in this case is the end of our function. Save and test that out. And if I keyboard interrupt now, it just says something went wrong. And even though our code ends there, because that's all the code we wrote, it ended gracefully. It didn't crash to exit. But what's the point of these examples? The try except, generally speaking, means that a function that would normally crash doesn't have to crash the entire program. We can handle that error internally to that function and then just keep going. So as an example, instead of just running this split bill function on its own, let's consider this as part of a larger program. So this function needs to return a value so that some other function, some calling function, can use that value. So rather than printing error messages when something goes wrong or printing the value when something goes right, we'll have this function return values. So returning the result or otherwise some default value. And that value then can be used in the calling program to do whatever it's doing. So let's start by creating the calling program. Put it down here. We'll call this calculate bill. So this calling program, it's going to get the amount of the bill, call split bill function to do the splitting, and then print out the result. So a really simple program just to demonstrate the chain of operations with multiple functions and try except blocks in the mix. So def calculate bill takes in no arguments, and this will start by asking the user to enter the amount of their bill. So I'll say amount equals input, enter the amount of your bill. And here we'll assume the user is going to enter some floating point number representing the dollar amount of the bill that they've received. So we can just cast this to a floating point number with the word float. For this simple demonstration, I'm not going to add another layer of try-catch just to keep the demonstration a bit clear. So assuming good inputs for brevity for now. But for a larger program, anytime you cast an input, you're going to want to check that that's an allowable thing. So wrap that in a try statement, and when it happens, it's fine, and it doesn't happen, handle it appropriately. For now, though, we'll assume good inputs, and then we'll take this amount and pass it into our split bill function, which is demonstrating try-catch for us. So we'll say the final cost is equal to split bill given the amount that we've gotten from our user. So we'll call split bill, we'll give it the amount, and we'll store whatever it gives back as the final cost. So in the best case scenario, everything went right and we get the result back. So in that case, we'll say print, use an F string again, your final bill is $ squiggly, final cost 0.2F each. So now for this to work, our split bill needs to return a value. We don't need to format our print statement here, so now we can just say return result. Simplifies that a bit. But in the cases where we run into some exception, these also need to have a value, right? If we only say print, but we're still saying final cost equals whatever comes out of split bill, but nothing was returned in those cases, then final cost will be none. So it'll say your final bill is, and then just none, or possibly an error because of the conversion. So let's also include some return values here. In the case where they gave us a bad value, we'll say return -1. We can have a different value for different types of errors. So for example, if someone divides by 0 people, you had 0 people there, each person owes $0. Doesn't matter how much money was charged to the table, no one's sitting at the table, then no one has to pay anything. So it makes sense in this case to return 0, for example. And in all other cases, we'll just say return -1 as a symbol that this code didn't work correctly. Now back out in our calling function, final cost is either the result that we're supposed to get, so the amount divided by the number of people, or it's either -1 or it's 0. So in the case that it's 0 or that it's result, we can just print out your final bill is either $0 each or result dollars each. In the case that it's -1, we don't want to do that. So we'd have an if statement here that says if final cost does not equal -1, then we'll print it as good. Otherwise, we have some sort of error, so we'll say print, there was an error splitting your bill. And then just so that the users get some sort of information back, we'll say print the total amount is, and then we'll print that out as a dollar amount as well. So $, that was AMT 0.2F, and this whole thing needs to be an F string so that we can do that. Okay, so now instead of calling our split bill function, we will call the calculate bill function, which doesn't take in any arguments. Save and run our code. Now it asks, what's the amount of our bill? So I will say 120 this time. I should probably put a space in there. Next time through it'll look nicer. 120, and it asks how many people. Let's say there were 8 people at our table, and your final bill is $15 each. So good inputs, everything works to completion. Calculate bill, call split bill. Split bill does the splitting, returns the information, and we print out the result. And now we try it without good values. So again, our calculate bill function, we're assuming good values, so I'll still say 120 is our amount. But for our split bill function, which is demonstrating our exception handling techniques, let's put in a bad value. I'll say hello again. So it says that's not a number. There's an error splitting your bill. The total is 120. So when we called split bill, even though this crashed, we still got back a number. That number in this case was -1. So our code continued on handling that value as necessary. If I run it again and give it some value, but then I use a keyboard interrupt in our split bill function, it says something went wrong. There was an error splitting your bill. The total amount is 1, 2, 3, 4. So it still recovers from our keyboard interrupts, or similarly, if I do, there are 0 people, it says no zeros, your final bill is $0 each. So even though our code can reach all these different types of exceptions while it's inside the split bill function, the outside calling program can still operate normally, as long as all those errors are contained within the split bill function because of our try except exception handling. So sometimes you'll use exceptions, sometimes you'll use if statements. The question might arise, when should you use one versus the other? The method to choose depends on how often you expect the event to occur. It's recommended that you use error checking, that is to say with if statements, when the event or error is very likely to occur or it's part of normal functioning. This is because always jumping into the exception code can be quite costly. You should use exception handling, though, when the error is unlikely to occur. That way, rather than wasting time checking for these very unlikely errors, the exceptions can work as a safety net. So that's exceptions in a nutshell. For the rest of this video, we'll do some more examples to get more experience working with exceptions. So as I had mentioned in a previous video, there is a string.isDigit function which determines whether or not a given string could be converted into an integer safely, but there's no such function for floating point numbers. In Python, for some reason, the accepted way to solve this is to use exceptions. That is, when converting into a float, we understand that one possible outcome is a type error if our inputs aren't as expected. So we wrap that in a try except. So to demonstrate this, let's make an isFloat function that uses this method. So we'll say def isFloat, all lowercase, so it matches the odd notation of the isDigit function. Let's put a comment here just to describe what this will do. So our inputs are going to be some string, and our output is going to be a Boolean, which will be true if our input string, which we'll call s, can be safely converted into a float. So the way we do this in Python is we'd say try. We have some string s. We want to convert that to a float, so we'll say float s. Convert to a float without checking. And if that works, we'll return true. So if there was an error on that line, we won't reach this next line because we jump down to the except block. But if there's no error with converting to our float, then it's safe to do, so we'll return true. Now, if there was an error converting that float, it would be a value error. I can say except value error, and in that case, we would return false. Note in your own applications, this function would be a bit redundant, as you could just adopt the try except code directly into your work, rather than calling this function, which attempts to convert the float already, and then if it's successful, returns true so that you can do it again in the calling program. But this should demonstrate what we need to at least. So I'll say python-i exceptions. And now I'm in Python interactive mode with all this stuff loaded, and I can say isFloat the string 3.14, and that's true. If I say 3.1.4, that's false. I say isFloat 3, that's true. IsFloat the word 3, and that's false. And finally, let's return to our rock, paper, scissors example to put all this information together. So we just modified this code to allow for a high score file, so it saves the file between executions of this code, so the high score persists between runs of the game. But what happens if the high score file goes missing? So our high score file here is called highscore.txt, and if I were to just delete that, what happens when I run my code now? Python RPS, and our code crashes. So we get a file not found error on line 47, no such file or directory, and then the name of our high score file. So let's go down to line 47 here. That's where we said get high score, it says with open our file name as file, and that didn't work because the file doesn't exist. So if there's no high score file to read at the start where we go to represent this to the user, then our code just crashes. So we can fix this with a try block. So we can just say try, and then take all of the operational code and tuck it into the try block. This is all the stuff that's supposed to happen in the best scenario where nothing goes wrong. Now, if that doesn't happen, if something goes wrong, like for example, the file doesn't exist, then we need to catch that. And the type of error we got was a file not found error, so we can catch that specifically, file not found error. And I'll take that one with a label as well. So I'll say file not found error, and I'll just call that E. So now inside this except block, we know something went wrong. The thing that went wrong is that the file wasn't found, because that's what causes a file not found error. And the description of that error is now stored in this variable called E. So what we can do is print E if we want to see that. Save and run our code. So now when we run our code, it says error, no such file or directory, data high score. So it printed out the error when we printed E, but notice then it continued on with the rest of the game. It said the current high score is none, and then rock, paper, scissors. So it's asking me to actually play the game. So keyboard interrupt to go back to the terminal here. Printing out the error is not the most useful thing for our get high score file. If we went to open the high score file and it didn't exist, a better way of handling that error would be to create a new file for our high score with default value so that our system can continue to operate with some base high score value. So where we printed the error before, we don't need that because that's a bit of a debug line. And instead we will create a new file, put a default value in that file, and return that default value as the current high score. So to make a new file, we can just say open the name of our high score, so high score file name, and then open that in write mode. Remember, if the file doesn't exist, which is something we know to be true, write mode will create the new file. Now, if we've opened this file, we want to actually put a value in there so that there is a default high score. So we'll say with open this file as, I'll just call it f. Then we can say f.write, and we'll put some default value. So we'll say -1000. That should be a very easy score for someone to beat, even if they're using weak throws like paper. Once that's done, our code, the rest of our program, still needs the high score current value, so we'll return that same value to the rest of the program. We'll say return -1000. So notice in either case, in our try case we're returning score, and in our accept case we're returning some score. So no matter what happens inside this function, outside of this function we're going to have some integer returned to us. So I'll call this a default value so the program still works. Let's test it out. Save, run our code. The current high score is -1000, and notice it created the new file there. And now when I run the game, trusty rock, wins every time, stop while I'm ahead, new high score. And now when I run the game, the current high score is 1. And now we've added file IO to our rock, paper, scissors game and made sure it was safe to do so. That's it for this video. We've covered the fundamentals of exceptions here. So we learned that when something might go wrong in our code, we should wrap that in a try block so that we can separate the default process of our code from the code that needs to handle that when something goes wrong. That's it for this video. It's also it for this chapter, so I will see you in the next video.